Alright, so guys, let's try to tackle the problem of a spherical charge. How do you calculate the electric field of a spherical charge at this level of physics, right, in electromagnetism? Well, guys, to calculate electric fields, you have two methods. One of them is Gauss's law, right? And the other one is picking a little dq on your charge distribution and integrating it, right? We had these 7 steps to solve that. Wonderful. But there's always a better choice between the two. For example, if I selected dq on this charge distribution, which in this case is a volume charge distribution. Let's read the question. What is the electric field created by the spherical charge with total charge q uniformly distributed across the volume? So volume charge distribution, which means when you selected dq, you calculate it using rho d volume, which is like a dx, dy, dz, or you can rewrite it in spherical coordinates. So basically this would, get you trying to calculate the components of the electric field in a triple integral like dx, dy, dz. So it would be very hard, though doable by selecting, a disk charge as your dq, which is still not as easy of a method. The easiest way to tackle this problem is using Gauss's law. So I'm going to solve this problem using Gauss's law. So I want to find the electric field at a distance, some random distance, small r, let's say, at this point P, right? The radius of the sphere is given, r. The charge is given, q. So how do I find the E field at this point P, let's say? Okay. So to be able to use Gauss's law, I need to have an idea about the direction of the electric field the sphere is creating. Since there is a spherical distribution, spherically symmetric charge distribution, it's just like a point charge's electric field, radially outward in all 3 dimensions. Okay, radially outward from the center of the sphere. That's what the E field lines look like outside. Beautiful. So we can use Gauss's law then if we can predict the E field lines and they look very symmetric, right? Then I can define a Gaussian surface. And what were our criteria? We want a Gaussian surface that will allow us to get rid of this integral, which means there is a dot product here. I need a fixed angle between E and dA. Also, I want the E field to be uniform on that surface. And the only way I get that uniformity is if that surface is the same distance to my charge. If I have a sphere, only surface that will give me a constant distance to the charge or charge distribution is another sphere. So I draw an imaginary sphere around the sphere, spherical charge, passing through my point P. So this sphere has a small radius r. It's centered at the center of my spherical charge. Okay. Now I can use this imaginary Gaussian surface to calculate the E field on this surface. Wonderful. So let's make the arguments again that, okay, assume this is a sphere. I just stole the picture from the previous example. So if this is a sphere, its electric field lines are spherically symmetric. They're radially outward in all 3 dimensions, right? So again, if you pick little areas on this Gaussian sphere, this is the Gaussian sphere, the black one. If you pick little areas on the Gaussian sphere, they're going to have little dA vectors. If you pick this little location, it has a little dA vector radially outward, perpendicular to the surface of the sphere. And that's also the direction of the E field at that particular point. Move on to a different location. Here, let's say the E field is perpendicular to the surface, which makes it radially outward. E field is radially outward. They're all parallel. So all of these E's and dA's are parallel. Also, this Gaussian surface gives me a uniform E. Why? It's the same distance to this charge distribution. So all of these E field numbers are the same. So uniform E field. This is how I know that I made a good choice. So let's move on to the calculation. Because in this calculation, this Gaussian surface, this imaginary surface choice, is going to allow me an easy flux calculation. First of all, E's and dA's are parallel, hence this dot product will bring a cosine of 0, which is 1. So this integral reduces down to E times dA instead of E dot dA. And E field is uniform on the surface, which means I don't even need the integration. So the whole flux calculation is E times area of the sphere. So let's go ahead and write it down. So the flux is E times area of the sphere. My Gaussian sphere, I wanted it to have a radius of small r. So total flux through the Gaussian sphere is E times 4 pi r squared. This is equal to the charge inside my Gaussian surface divided by epsilon 0. I'm including all of the charge in my Gaussian sphere, so it's big Q that the problem gives me divided by epsilon 0. Hence, the E field of the spherical charge with volume charge distribution uniform is Q over 4 pi epsilon 0 r squared, same as the point charges. There is the answer. Okay, what if now, hold on, why do I have the same thing? Okay. What if now I want to find the E field inside this insulating sphere? Well, why did I just call it insulating sphere? The problem didn't tell me that. Well, guys, if this was a conducting sphere, it would not have charge in its volume. The charge would collect only on the surface. So if there is charge inside the volume of the sphere, then it's an insulating sphere. So what if now I carry this point P to the inside of the sphere and I want to calculate the electric field inside? What do? Well, use Gauss's law again. How can I use Gauss's law here? Well, guys, remember outside we drew a sphere for several reasons. One of them being the points on the surface to the points on the surface would be the same distance to the charge. For that one similar reason, we could draw another Gaussian sphere passing through this point P in the inside of the spherical charge, right? Why? Because all of the points on my Gaussian surface would be the same distance to the charge, on the inside or on the outside, okay? Hence, I would have a uniform electric field on this surface as well. Let me draw it and see if it works. So if my calculations are going to, or my assumptions are right, the charge inside my Gaussian sphere are going to contribute to the electric fields that I'm trying to calculate. Hence, the charges inside my sphere, which is a spherical charge, will contribute to the electric field calculation. Hence, the direction of E field that these guys are going to generate, they will be like a spherical charges, so they will be radially outward again. So I will again have a radially outward E field, which means my E field vectors again will be coming perpendicular to the surface of my Gaussian sphere. Hence, E's will be parallel to my dA's again. So I will have 0-degree angle between E and dA. Also, they will be the same distance to the charge, hence the E will come out of the integration. So all I need to do again is to calculate an E times area of my Gaussian sphere. So E times 4 pi r squared, small r being the distance to the center from this point P, which is now the radius of my Gaussian sphere. So E times 4 pi r squared for flux. Now let's get to calculation of Q in. This is the only tricky part in this question. What is Q in? Well, it's all of the charge that remains inside my Gaussian sphere. So this time I cannot write the total Q as my charge. I need to use the volume charge distribution. So any charge, any partial charge is going to be volume charge distribution rho times the volume that I'm considering. So here it's going to be the volume of my Gaussian sphere because this is the charge that I'm enclosing. And its volume is 4 over 3 pi small r cube. That's the volume of my Gaussian sphere. Wonderful. What is rho? How do I calculate rho? Well, it's charge divided by volume. So I have a total charge big Q distributed across the volume 4/3 pi big R cube. That's the volume of my insulating sphere. So Q over volume gives me rho. If I multiply that with the volume of my Gaussian sphere, or volume enclosed by my Gaussian sphere, there I have it. I have a Q in. Canceling out 4/3 pi's, I have QR cubed divided by big R cube. Wonderful. So if I plug this in now, I will be done with the question. E times 4 pi r squared is equal to Q times small r cube divided by big R cube. Pulling E out of this equation, right? R squared cancels with this R cube, leaving an R. So E is equal to Q times R divided by 4 pi epsilon 0 R cube. Wonderful. There we have an answer. Electric field at a distance small r inside the insulating sphere.